All right, this is Lab 9, optical testing with a Shack Cube interferometer. I'm Winona Escher.
I'm Ian Winsky.
I'm Caleb Cook.
I'm Logan Pulaski. Let's get into it. This is why in the photo shown right here, you can think of the shear plate interferogram as just being a shifted overlay of the Shack Cube interferogram, and that's illustrated because in the Shack Cube interferometer, you have those concentric rings, but then if you have another reference wavefront that's shifted onto it or overlaid, then it's going to look like the one you see on the left.
Shack Cube interferometer is a modification of the laser-based physio that can be used to test the surface figure of concave surfaces. The advantage of this interferometer is that only the curved surface on the Shack Cube beam splitter needs to be of high quality, since every other optic is a common path. In order to test lenses or convex surfaces, additional high-quality optics are required, but this interferometer is lower cost than a Twyman green or regular physio, but not as flexible.
A Shack Cube interferometer measures the wavefront errors directly, whereas a shear plate interferometer measures the wavefront error difference function by comparing the aberrated wavefront with the sheared version of itself.
So to improve fringe contrast and reduce secondary fringes, we first want to make sure that we have everything aligned very well. So we want the interferometer, the viewing screen, and the unit under test all aligned along the same axes. And then we can also adjust the polarization of the laser source to optimize the fringe contrast. So here we have the Shack Cube interferometer. We've aligned the spatial filter to the axis of the laser and the microscope objective. And we've identified that the output beam directions focus is actually at the face of the cube here. We have the null fringe here. This is the zero order fringe in all of the circular defocus rings that we were seeing, and we can't quite get rid of it. It's actually very sensitive if I bump this micrometer adjuster here. But as we sort of zoom in on it, we can see that the fringe is still muddled and there's some distortions in there. We're at our null fringe and we're going to add defocus. What we would expect to see if this was a perfect aberration-free system is only defocused fringes, meaning that we would have concentric circles equally spaced or equal thickness. But because this is a spherical mirror, we're probably going to see spherical aberration in there also.
For the long focal length test mirror, we added defocus in increments of 50 microns and counted the fringes present from the null fringe, and we found that this was a linear relationship.
To try to interpret what aberrations are present here, it seems like it's probably a combination of spherical and defocus, because we can see a zero order fringe in the middle and then a singular fringe on the outside here, which is fairly consistent with spherical and defocus. But together, you get a really thick fringe for that first fringe outside of the zero order.
Back to our null fringe. We are now going to add some tilt, and we are expecting to see straight lines.
You can see here on our fringes, they are straight, which agrees with our prediction, but they are not equally spaced. They're about equally spaced, but they're not, because there's probably some spherical aberration in our system. The local defects in here are probably due to defects on the lens, such as chips or surface height errors on the lens. And then the curvature is likely a combination between defocus and spherical aberration. Spherical aberration contributing to the fact that the fringes get closer together as you move outwards from the center.
Rachel, if you added defocus and tilt to your mirror, what kind of fringes would you expect?
No, I'm not being featured in the video right now.
So what she said was you would see concentric rings, but just shifted.
So now we are going to tilt the mirror about the vertical axis and then induce some defocus. So by tilting it, we should be able to see these straight fringes with even spacing. We are going to add a little bit of defocus. Oop, where'd it go? There it is. And as you can see, the fringe spacing gets smaller and it is tilted to the left.
You can see concentric rings that are shifted. Woohoo! Whoopee!
Okay, so now we have our short focal length mirror set up and aligned with our Shack Cube. We are going to add some defocus and see how the fringes change.
For the second mirror, we added defocus in increments of 50 microns and counted the number of fringes after the null fringe, and we found this relationship to be more exponential.
Here we have our 100 millimeter focal length mirror, and we've induced tilt about the vertical axis, and we can see that we have our zero order null fringe over here, and then we have our waves coming out this way, about as vertical as we can get them. And we have our first thick fringe here that's associated with the defocus and spherical aberration, and then the fringes get thinner and they come more rapidly as we progress. So this would be indicative of the spherical aberration and tilt. We've added defocus and tilt, and so you can see the zero order fringe, the big chunky spherical and defocus aberration ring in the middle right there. And then as the fringes go off to screen right, we see that there's a lot more fringes in that direction, indicating tilt about the vertical axis. And we can also see that the fringes get closer together and thinner, indicating spherical aberration.
All right, so now we are going to be building a Shat cube interferometer to examine aberrations and do some simple fringe analysis in Zemax.
So in Zemax, we downloaded an uncoated aspherical lens from MN Optics with an effective focal length of 15 millimeters. This was created in a sequential file, which was then imported into this non-sequential ray trace. So first we created our collimated source, passing through a focusing lens, and then we created our cube beam splitter, which was then turned into a Shat cube beam splitter, which is shown right here. Our testing mirror is up above, and then we place a detector down below. And in this way, we can use the detector viewer in this non-sequential ray trace to look at our interference pattern. So right now, we are looking at our null fringe because on our test mirror, labeled right here, we have no defocus, which is done by adjusting the Z position. We have no tilt about the Y-axis, and we have not changed our conic constant past 0, so there should be no spherical aberration, and this is what the null fringe looks like. This slide contains the interferograms of 5 defocus measurements. So starting with our null fringe with no defocus, we then defocus by 50 microns, which is shown in the top left photo. And then we continue to defocus by 50 microns until we reach 250 microns. And we can see that this trend with defocus is that as we slowly add defocus to the mirror from the best focus position that our null fringe is at, there are more fringes, but the spacing stays the same as we continue to add defocus. So we see at 250 microns there are a lot more fringes, but the spacing stays the same. We then analyzed our interferograms when tilting about the Y and X axes. On the top row here, those 5 images represent tilt about the Y axis, where we vary the tilt by 0.002 degrees at each step, up until 0.01 degrees on the very right. And then the bottom row is when we tilt about the X axis. And we can see that at the best focus position, so with no defocus, as we slowly add tilt to the mirror, the total number of fringes increases as we add tilt, and the fringes get closer together. The fringes do this in different directions based on what axis it's tilted about. So you can see for the Y-axis, the interferogram produces vertical lines, and for the tilt about X-axis, the interferogram produces horizontal fringes. In this slide, we showcase increments of tilt about the Y-axis in the positive and negative directions, while we are defocused 250 microns from best focus. The takeaway from this is that when we tilt defocused fringes, the number of fringes changes about the axis of rotation, and that's why it looks like there's this shift from the center. When there is more spherical aberration in our system, which is done by increasing the value of the conic constant of our testing mirror, we find that there are more fringes, which come in the form of concentric rings that are closer together as we move away from the origin. Once again, when we add tilt to a spherically aberrated system, there are more fringes about the axis of rotation as we increase the tilt in that direction. And then the combination of spherical aberration, tilt, and defocus is shown here.